First mate Philippe Lejour was standing on the bridge when he saw a wave nearly 7 times larger than any other appear seemingly out of nowhere, heading for his ship. Near the moment of impact, Lejour captured the monster on film.
That shot of a rogue wave was one of the first pieces of evidence out there to an unbelieving world that rogue waves did exist, a wave that literally is dwarfing this huge supertanker.
The top of the short mast on the starboard side measured 82 feet above the sea. Based on this height, the rogue wave was estimated to be 100 feet tall.
Now, at last, there was photographic proof. They had to sit up and take notice. Steadily, the reports not only began to come in afresh, but began to become accepted.
The crew of the Languedoc survived a crushing blow that hit the ship from stem to stern. But 2 years later, the crew of the oil drilling platform Ocean Ranger was not so lucky. Storms in the North Atlantic are some of the fiercest in the world. The Ocean Ranger, operating off the coast of Newfoundland, Canada, was built to handle even the most extreme conditions. The 35-story tall rig was the largest and most advanced of its kind. Weathering a 40-foot wave was nothing to the Ocean Ranger. On February 14, 1982, a rogue more than twice that size, a rogue nearly 90 feet tall, smashed through the windows of the control room.
When you hit a wall of water, it's like hitting a wall of concrete. That's the force of the ocean.
The rogue wave flooded out vital computer systems. The ballast tanks, which normally stabilized the rig, malfunctioned. The platform was thrown out of balance and capsized. All 84 crewmen were killed. It was the worst death toll on record for a rogue wave disaster.
It's still remembered to this day in Newfoundland. People talk about it all the time. Not only because of the loss of all those lives, but because of the power of a single wave to take this massive and powerful platform and send it down.
Even with so much death and destruction, there was still doubt about the actual size of these waves. Then, in 1995, a massive blow to another oil rig provided the first scientific measurement of a rogue wave. The Dropner drilling platform stood in the North Sea between Norway and Scotland. On New Year's Day, 35-foot waves pounded the rig, rough but not unheard of. Suddenly, a wave nearly 3 times larger took dead aim at the Dropner, bearing down at 45 miles per hour. When the wave hit, a laser mounted on the platform captured the first ever definitive measurement of one of these monsters. The wave topped out at 91 feet.
That kind of empirical scientific evidence was one of the important steps in getting the rest of the world to recognize that rogue waves existed, that they could be this high, and that it wasn't just a sailor superstition or an excuse for bad seamanship.
It was only when the Dropner wave was measured that a captain could say that he encountered a freak wave without being called a drunkard.
Oceanographers were able to analyze the wave patterns before, during, and after the Dropner wave, and the results were startling. This is the wave pattern taken over a typical 20 minutes during the storm. The waves vary in height, but still fall within a comparable range. But this is the pattern surrounding the giant wave. From this data, scientists were finally able to assign a definition to a rogue wave. It is a wave at least twice the size of any other wave in the area. A single startling event, unconnected from other waves in the pattern. A true rogue.
Basically comes out of nowhere. You don't see them coming. And at night, it's even worse.
This answers what a rogue wave is. But the answer to what causes a rogue wave is more of a challenge.
Here it comes. Follow that
one. Using laboratory wave tanks to simulate conditions in the ocean, scientists are learning how rogue waves might be formed.
The rogue wave is first of all, driven by the wind, but modulated by the current.
When strong currents collide with waves moving in the opposite direction, the wave can suddenly become compressed, thrusting it upward, forming a rogue wave. This may explain why areas of the ocean known for strong currents seem to be breeding grounds for rogue waves. The Gulf Stream is one such current, and it runs right through the infamous area known as the Bermuda Triangle.
There is a possibility, there's a probability even, that many of the losses, the unattributable, unexplainable losses in the Bermuda Triangle come not from the forces of the supernatural, but the force of the ocean to generate rogue waves.
Remember, rogue waves by definition don't play by the rules. And the wave tank shows they can also form when currents and waves travel in the same direction.
One of the things that can lead to really large waves forming on the ocean is when waves with different wavelengths meet, overtake each other.
The energy of the merging waves suddenly combines, becomes focused, thrusting a new wave higher. Rogue waves can also form when normal waves meet obstacles, such as islands.
You have waves propagating towards this island here, and as they get blocked by the island, they split and they have to travel around it.
The waves wrap around the island and come back together on the other side, stronger and more deadly.
If you happen to be right here in this part of the island, you could encounter a rogue wave.
The Agulhas Current off South Africa, where the Atlantic and Indian Oceans meet, is a notorious breeding ground for rogue waves. Here you have strong currents, opposing wave patterns, and also underwater obstacles far beneath on the ocean floor.
As an example, here I have a simulation of what is called a shoal, which is just a hump on the seabed. And let's see what happens when waves propagate over this hump. This is the sort of phenomenon that could explain why in some places, like off the coast of South Africa, where there is a plateau and there is refraction and diffraction and bending of the waves so that they converge in certain areas, and it could be creating very big waves in certain places.
And there is another condition under which rogue waves form. It is the most insidious of all monsters. The wave that occurs where there is no island, no undersea shoals or plateaus, no crossing currents, only calm seas, and still a monster wave rises up without warning. A monstrous water mountain, towering 100 feet above you, crashing down with enough force to submerge a luxury liner in a matter of seconds. Difficult to imagine, but photos of storm-generated rogue waves prove these monsters do exist. Now, consider this. The same kind of wave with the same power appearing out of a calm ocean on a cloudless day.
I never really believed in rogue waves before. It was something that we would joke about on the bridge of ships. If somebody would slip over the side or something, we joked that, oh, rogue wave, and that's what happened. But now I've changed my point of view.
Rogue waves happen even in calm seas, and in some cases, they're generated by storms hundreds of miles away, pushed and whipped by huge winds. These waves will build up to incredible height, and then as they move out of the storm, continue on, even across a calm sea, to strike someone out of nowhere.
November 4th, 2000, Point Arguello, California. Just such a swell, generated by a distant storm, slipped silently through calm Pacific waters toward the research vessel Ballena. The Ballena was built to handle rough seas, and Mark Pickett was a 20-year veteran of NOAA, the National Oceanic and Atmospheric Administration.
It was a flat, calm, beautiful day off the Central California coast, and I certainly would have never expected that I would run into such a large rogue wave, and it would change my life.
The captain's assessment of the wave might have gone down as another tall tale from an inexperienced sailor, but Pickett had impeccable credentials.
I operate research ships for NOAA, and I'm also a scientist. I have a PhD in oceanography, so I also do science for NOAA.
Also on board the 60-foot vessel with Captain Pickett were scientist Dr. Guy Cochran and electronics technician Michael Boyne. The usually turbulent waters were calm. The wind was at 10 knots with only 4-foot swells.
I had both doors to the bridge wide open, and I had just taken off my flotation jacket because it was getting warm. When I looked out the port window, I saw a large wave coming our way, and I turned the boat into the wave and punched the throttles. And I absolutely expected that I should be able to punch through this wave or ride over this wave.
But at 20 feet, the rogue wave was 5 times larger than any other wave in the surrounding area. And the speed with which it hit didn't leave any time for maneuvering.
I hit it about a 30-degree angle, and it picked up the bow of the boat, and it flipped and twisted at the same time. In an instant, we were upside down, and the ship filled with water.
Pickett's fellow crew members were below deck, underwater, struggling to get out. The bridge doors were wedged shut by the wave's impact.
I kept trying to push it open, and I, of course, was panicking as I wanted to get out of there and I was running out of breath.
By sheer will, the 3 men eventually made it out and into a small life raft. But after paddling for nearly an hour with only 1 oar between them, they agreed their best chance for survival was to swim the short distance to the shore.
The water was cold. We had all our clothes on. We were exhausted from escaping from the overturned vessel and trying to paddle. And once I got to shore and I turned around and looked back out, the 2 other people that were with me were not making it. And they were in the process of going under and drowning.
There's no more terrible thing in the world, particularly to be the captain, to be the person in charge, to be responsible, to look out there and to see somebody dying and to know that you have to go. There's an old saying in the Coast Guard, you have to go out, but you don't have to come back.
Captain Pickett did go back out and rescued both drowning men.
So the 3 of us survived the incident with minor injuries and the loss of the vessel, but no loss of life.
For his heroism, Captain Pickett was decorated with the highest honor from the U.S. Department of Commerce.
The people, especially the mariners who have survived freak waves, are quite traumatized. Even many years after the event, they really do have post-traumatic stress disorder. That's how terrifying the experience is.
You think you understand the ocean, you think you have the respect for the ocean, but you never think that something like this will occur and turn your world upside down, nearly kill you, and nearly take away a couple people's lives who were depending on you. And going through that and living that is it's a difficult experience, and it's difficult for me to think back and to go back over it. It's amazing power in the ocean for something just to come out of nowhere and completely destroy a boat in a matter of seconds.
After incidents like Mark Pickett's trained observations about the rogue that destroyed his research ship, the scientific community accelerated their efforts. Could similar freak waves explain some of the great unexplained shipwrecks of the past? Could the mythology of the ancient mariners have a basis in the reality of rogue waves?
In the past, you're sailing along in a small wooden vessel and suddenly this massive wall of water comes along, and if you live through the experience, you have to have been filled with a superstitious awe and a fear. What could have created this? This is where the idea of the sea monster comes from. Some creature from the depths, smacking the ocean with its tail, moving in a vast amount of water with the bulk of its monstrous form. This is what made rogue waves in the minds of ancient mariners.
When you start looking for clues through marine history, you find them.
1951, the North Atlantic. Captain Henrik Carlson radioed that his cargo ship, the Flying Enterprise, had been hit by a force he cryptically referred to as a heavy sea. At the time, he did not call it a rogue wave. Carlson didn't want to be written off as just another drunken sailor.
His ship cracked amidships. A crack appeared, as if somebody had taken a meat cleaver and hacked down on the ship, right in the middle of the ship.
Carlson and his crew managed to shore up the ship enough to keep her afloat.
Carlson had the wit to send his men out to start winching the ship with wires closed from one set of bollards to another. And when he got them closed by about 3/4 of an inch, he then stuffed that crack with concrete and had them build a breakwater over it. Amazing.
The ship stayed afloat, but 28 hours later, the Flying Enterprise was hit again by a second rogue wave, believed to be 65 feet high.
The mast snapped, all the radio antennae went. The actual metal plates of the ship cracked. That is an indication of the sheer force. It's like liquid hell breaking loose.
40 crew and 10 passengers were rescued, but Captain Carlson stayed with his ship and maintained radio contact.
There were some terrific mountains of seas there. I don't know if you were in the same one, but it was nothing but seas and water all over the place.
British tugs tried to tow the battered ship 400 miles back to Falmouth, England. But only 37 miles from shore, the Flying Enterprise succumbed to the sea. Captain Carlson jumped from the ship only minutes before it went under. Back home, he was greeted as a hero. His belief that he had been hit by not one, but 2 rogue waves, he kept to himself.
Part of the reason why the rogue wave didn't become respectable for a very long time was because sea captains didn't want to admit to having been overpowered by the weather. They're very proud of their skill, and rightly so. But then it became evident that it was never their fault. All the skill in the world isn't going to save you there.
Captains not only face rogue waves on the oceans, the Great Lakes are another hot spot and the scene of one of the most famous shipwrecks in history. November 10th, 1975, the Edmund Fitzgerald, a freighter carrying supplies for the steel industry, ran into a horrendous storm on Lake Superior.
The Great Lakes of North America literally are an inland sea, and every mariner that sails them knows that. They build up waves that equal anything that you'll find out in the open ocean. So it'd be no surprise then to most to learn that there are rogue waves on the Great Lakes.
At nightfall, the Fitz, as she was known, suddenly ran into trouble. Storm waves knocked out her radar and damaged the ship. Her captain, Ernest McSorley, told a nearby ship, the Arthur Anderson, that he was in trouble but in control. The Anderson reported back that 2 large waves were heading toward the Fitzgerald's location. Then, in just a matter of minutes, the Fitz disappeared, as did all 29 crew members.
The last contact we had with him, he said, well, he was going along fine and holding his own and no problems. And then when we couldn't see his lights, we figured we should be catching him a little bit because he'd checked down and then he just didn't wasn't there.
And it is possible, if a rogue wave struck the Fitzgerald or if 2 struck, that it literally would have torn her in half and sent her to the bottom.
6 months later, the United States Coast Guard found the wreck of the Edmund Fitzgerald at the bottom of Lake Superior. It was split in 2.
The Edmund Fitzgerald was found at 500 feet of water, and she was completely mangled. Now, what kind of force did that? What kind of weight of water? What kind of energy? What kind of massive nuclear force made of water and wind ripped a ship that strong apart so completely?
The Coast Guard was unable to definitively say exactly what sank the ship, but in more recent years, the National Oceanic and Atmospheric Administration has documented rogue waves in the Great Lakes. And in that area off Whitefish Point where she was lost, there you can have the kind of forces that would build up to create a rogue wave.
The re-examination of historical shipwrecks was yielding alarming data. Naval architects studying ship disasters between 1969 and 1994 found that during those 25 years, 60 supercarriers went down due to sudden flooding. On closer study, it was determined that more than a third of the sinkings were probably caused by rogue waves. To try to head off new disasters, scientists needed to figure out the frequency and location of rogue wave strikes. Monitoring the world's oceans was virtually an impossible task until the early 1990s, when the European Space Agency launched twin Earth observation radar satellites, ERS-1 and 2. With satellite technology, international research facilities can precisely pinpoint a particular part of the ocean and map wave activity under any conditions.
This satellite is a radar satellite, therefore it has the capability of imaging the sea surface even at night and through the clouds. So that is very important if you want to see very high waves, you want to be watching the sea surface in storms, and so therefore a radar satellite is the optimal instrument to do that. And then we use these images and translate them into sea surface height, and we investigate the wavelengths, the crest lengths, the steepness of the wave, and the maximum wave height.
The results of the satellite research have been startling, smashing the mathematical model suggesting a 100-foot rogue wave is a once-in-10,000-year event. For example, studying a 12-year period of wave activity in the area of the North Sea where the Dropner oil rig was hit, researchers measured 466 rogues. Then, in 2001, two cruise ships traveling around the Horn of South America, the Caledonian Star and the Bremen, were both struck by rogue waves in one 10-day period. In each hit, the wave smashed into the ship's bridge over 80 feet above the waterline. Scientists analyzed global satellite ocean data for the 3 weeks before, during, and after the Bremen and Caledonian Star incidents.
Within a 3-week period, looking down from space, they plotted 10 rogue waves higher than 75 feet traveling in the world's oceans at the time these two cruise ships were hit.
The largest waves that we found on the images in these 3-week time series were between 90 and 105 feet. The coincidence of the Bremen and the Caledonian Star, that was the turning point for us to believe that freak waves are much more frequent than we anticipated before.
The satellite and radar imaging is being compiled into a wave atlas, a map of rogue wave hotspots, where they formed, how long they lasted, and how far they traveled. In time, the wave atlas will be the foundation of an early warning system, pinpointing areas where new rogue waves may erupt, then routing ships on the safest and fastest route.
If you recognize that you have two different wave systems that will join at a certain point on the sea, then that you can warn for this and say that is an area that is particularly dangerous for rogue waves.
So with the warning from space, we would be able to forecast monster waves within 5 hours or so.
Besides satellite imaging, experiments are being conducted with alternative tracking and prediction systems.
There's also the idea of floating networks, buoys with intelligent computers that have the ability to learn, plot ocean currents, send warnings to each other, and create a neural net, if you will, floating on the sea to send out and broadcast exactly what's going on. That way, with that type of an early warning system, a ship several hundred miles away could be told, a rogue wave is coming your way.
While warning systems get more sophisticated, shipbuilders are also doing their part, designing and building tighter, stronger, more flexible vessels to withstand the force of a rogue wave, if it's even possible. strike without warning, seemingly out of nowhere. That is why the images we have of them are nearly all before and after. What we don't have, with a few rare and grainy exceptions, is what happens during the horrendous crash of a rogue wave disaster. The closest we can come is in the 2006 motion picture Poseidon. What would it look like if a 120-foot rogue wave hit a modern cruise ship broadside? That was the question director Wolfgang Petersen asked the visual effects wizards at ILM, Industrial Light and Magic.
I like ILM for that because they really want to go make it real. Not put some nice effect things together that look great, but this is how it happens. And they study it, and they do it in a scientific way, and when they figured it out then they make it spectacular.
The first step for ILM was to build the Poseidon in the computer. The challenge was to make the ship an exact replica structurally, down to the last rivet of a state-of-the-art luxury cruise ship, 1,100 feet long and 20 stories high, with 13 passenger decks. Then, working with a team of wave dynamic experts from Stanford University, ILM created a rogue wave 120 feet tall. Based on real-life satellite data and wave tank studies, the computer-generated wave was so realistic it provides nearly documentary evidence of a rogue wave hit. This was no simple challenge, since realistic water is the most difficult image to create digitally. ILM hired more than 100 software developers, engineers, and artists. They spent over a year developing a completely new kind of visual effects technology so advanced it replicates the patterns of how water moves and breaks apart right down to the molecular level. Then, to recreate the violent crush of water, Petersen and his special effects team decided there's nothing like the real thing.
The entire ballroom was flooded within a few seconds. This was not visual effects. This was 90,000 gallons of water flying through the windows. Quite amazing.
With visual and special effects artists, Poseidon graphically portrays what could happen in a rogue wave disaster on a real ocean cruise.
When you take a cruise, the first thing you notice as you go on board is how high this ship is off the ground, off the water. They are huge. And then you ask yourself, is it possible that a wave could knock this thing over on her side? It is absolutely possible.
And the damage that the movie wave causes to the computer-generated Poseidon is exactly what real-life naval architects are working very hard to try to prevent. Ships are a crucial component of the world economy. 95% of everything we buy gets to us by ship. And over 10 million people a year vacation on cruise ships. That's a big incentive to build ships that won't be crushed by large waves.
Ships have to be designed to accommodate that kind of force that can just lift a house up off its foundation and carry it away. A ship is expected to rise up over that and just continue on its merry way as if totally unaffected by that.
A 36-foot raging storm wave strikes with the force of about 6 tons per square yard. Most ships can withstand 15 tons without damage. But a 100-foot rogue wave strikes with a force of 100 tons, almost twice the power of an industrial car compactor.
Right now, naval architects build ships to a certain standard. That is, they know the type of stresses a ship's going to undergo in a storm, and they build to meet that and to exceed it in most cases. The question now is, should they build ships to withstand the force of rogue waves?
One of the biggest structural challenges for naval architects is when rogue waves strike high on the bow, smashing through windows on the bridge and upper decks.
Then the windows are hit and then break, and then the electronic gets flooded and the ship can't maneuver.
Redesigning the bridge and its windows to deflect these hits is one solution. The Queen Mary II, launched in 2003, is an example. The $800 million cruise ship was fitted with a thicker forward hull, an enhanced bridge screen, and more pronounced flare of the bow to protect it from large waves. However, these major structural changes still won't be enough if a ship's watertight hatches don't hold.
When a ship hits a big wave and it goes through that wave, we oftentimes call that going submarine. For a moment, you're not on the surface of the water, you're underneath it. You can pop on out again on the other side if you keep your ship watertight. And what's important in keeping it watertight is having every hatch closed. If a hatch fails, the ship's going to start to flood. And when it starts to flood, you lose that buoyancy. The most powerful pumps with enough hatches open to the sea will not counter the effects of flooding, and you'll go down.
To retrofit ships or build new ones to withstand all rogue waves will cost a fortune. Is it worth the cost?
It's an argument that will be renewed every time another vessel is lost to a rogue wave, and it's an argument that would rage just as it does on land after an earthquake, when people say, okay, we've built to this Richter scale, should we now build for the superquake? Maybe the question is not building to encounter, but finding the means with technology to avoid.
Even with its perils, man cannot resist the lure of the sea and will continue to return with incredible tales of the one that got away, the white whale, the giant squid, or the towering, crushing rogue wave.
Felt like a sledgehammer hitting the back of the boat, a large sledgehammer.
Literally looked like an alligator mouth. He had a gap from his bow all the way back to
Picked
about
our
an
bow
inch.
up and flipped the stem over stern. Extremely violent, extremely fast.
Tremendous force, the way it slammed down. You thought the ship was breaking apart. You really did.
These massive waves have been called monster waves, they've been called freak waves, they've been called rogue waves, they've been called ass-kicking waves, and I've heard it all. And it's the type of wave, when you hear about it, that you wish, you hope you never encounter.